Hi everyone. Right now we're going to go through the guided notes section of objective 4.3, which is to find inflection points and regions of concavity. This is going to be extremely similar to the previous objective, which was about finding critical points and regions of increasing and decreasing. So let's start with the notes. Remember, an inflection point occurs when concavity changes. So whether that's concave up to concave down or concave down to concave up, that's defined as an inflection point. And this usually means that the second derivative, f double prime of x, equals 0. The reason the word usually is important there is that sometimes the second derivative can go from positive to 0 and then back up to positive. And in that case, concavity doesn't change. It like almost does, but then it doesn't. So we don't classify that as an inflection point. The way we find this is very straightforward. We take the second derivative and we set it equal to 0 and solve. Then we make a sign chart just like when we were finding critical points. So let's start with finding inflection points. To find inflection points, we need to find the second derivative and set it equal to 0. So in this case, f prime of x would be 3x squared plus 10x minus 2. Sorry, that says 10x. And then the second derivative, f double prime of x, would equal 6x plus 10. And since we're looking for inflection points, we're looking for, excuse me, I'm doing this at school as you can hear. We're looking for when the second derivative equals 0. So I'll write equals 0 at the end of that. When I solve for x here, I subtract 10 and I divide by 6. I get x is equal to negative 5/3. So this is the only possible inflection point that we found. It probably is, but we need to double check using a sign chart. So just like with critical points, you draw a line that represents the x-axis. The only thing you care about is the value of negative 5/3, so x equals negative 5/3. And then what we want to know is this concave up or concave down on either side of this? And then we'll know for sure that it's actually an inflection point. So when we do this, we're going to plug into f double prime, and we need to choose a value below and above, just like normal. Negative 5/3 is between negative 1 and negative 2, so let's plug in negative 2 on this side and 0 on this side, and that'll tell us if it's concave up or concave down. And we're plugging it into the second derivative because we only care about concavity here. If you plug negative 2 into this expression, 6x plus 10, that comes out to a negative number. So that means that to the left of negative 5/3, this graph is concave down. When you plug in 0 into 6x plus 10, it comes out to a positive number, which means to the right it's concave up, which means this is indeed an inflection point. You probably could have guessed that anyway. It was the only option, but this verifies it. So everything that we just did here is kind of mental scratch work. You could have chosen other numbers other than negative 2 and 0, they just had to be on either side. So we have a graph that is concave down followed by concave up. I'm going to erase what I just did. It's not necessarily decreasing. I just wanted to show you what that looks like. So our only answer for inflection point is negative 5/3. Let's go on to the next example, which you notice is slightly different in that I gave you the second derivative instead of the first derivative. So we don't need to do these first two steps of finding the derivatives. It's already given. So we'll just write e to the x plus 3 equals 0. If you start solving this, you're going to notice pretty quickly it doesn't work. E to the x is equal to negative 3. And if you take natural log of both sides, sorry about my notation, but you get x is equal to natural log of negative 3, which just doesn't exist. So what this tells us is that there are no inflection points. And that's going to be the answer here. You might have noticed this earlier, e to the x is an exponential function that's always positive if you think about the graph. So if you take a number that's always positive and you add 3 to it, it's going to stay positive the whole time. In fact, this graph, because the second derivative is always positive, this graph is always concave up. It's concave up from negative infinity to infinity. I just realized that I probably should have written a little bit more on the left as well. So the other thing I'm going to write here for the regions of concavity, that this first example, the function was concave up from -5/3 to infinity, and it was concave down from -infinity to 5/3. So this all goes together with that inflection point as part of the same analysis. So to recap, set the second derivative equal to 0, find any possible inflection points, then check the second derivative to see when it's concave up and concave down compared to those inflection points. In this case, there were none, so it's just always concave up. And that's it.